All right. We just want to talk a little bit about what we're going to be doing in the lab. The first little bit is just to introduce you to some of the main units that we use for measurement in chemistry. Now, chemistry is a science. Science is all about measurements. So here are some of the more common measurements or units we're going to be using in the chemistry course. And the first table is just for you to look through and acquaint yourself with the different units, right? And the symbols for those units. Now, sometimes the symbols and the units are going to be a little bit different. Um, for example, if you take a look at electric current, right, down at the very bottom of your table here, it's a little bit different symbol than the name of the unit, right? So it does vary a little bit. All right, so the base unit and the symbols might be a little bit different in terms of the symbol and the name. Again, they're just a couple of units and measurements that are used primarily in chemistry, especially when we get to the solution section. So when we take a look at molar mass, volume, molar concentration, mass, those are some symbols that you should become pretty familiar with, right? And the unit associated with those symbols as well. So, for example, molar mass, capital M, grams per mole, and the symbol is sort of a shorthand of the unit. So, volume, V, that would be in liters, and the symbol would be L. So, again, a good idea to look these over and become familiar with these units and the measures. Now, everything that we're going to be measuring um, in this course is going to be using the metric system. I know that once we get into industry, there's still a couple of places that do use the imperial system, but that's becoming more and more rare. The industry is kind of moving towards the metric. That's becoming the language of science. That is the language of science currently now, using the metric system. So the metric system, the units are as we move from one to another. So we're usually accustomed to inches and feet. So 12 inches make 1 foot, 3 feet make 1 yard. So there isn't a consistent number of units required to move to the next bigger unit when we're talking about the imperial system. And that's what makes it really challenging. The metric system, on the other hand, as you remember, everything is in units, bases. Bases kind of move up every time you've got 10 of that particular base. So, for example, if I've got 1 meter, 1 meter would be the base measurement for length. If I had 10 meters, that would equal 1 decameter. If I had 100 meters, that would be 1 hectometer. If I had 1,000 meters, that would be 1 kilometer. So every time I increase by a factor of 10, I can move to the next level up. Now, we are also going to be using measurements that are smaller than the base unit. So again, sticking with meter as an example, if I were to have only 1/10 of a meter, okay, take a meter and divide it into 10 even pieces, one of those pieces would be a decimeter. If I were to take a look at a meter and dividing it into 100 even pieces, one of those pieces would be called a centimeter. So as I take my base unit and I break it up into smaller and smaller pieces, I can use different prefixes depending on how small I break it. I break that base into. So if we take a look at converting now, converting from one unit to another. So if I were to convert, for example, for my base unit, and again, let's use that meter as an example. So if my base unit here is a meter, then if I wanted to convert that base unit to the next higher unit above it, for every step I take, I would divide by 10. So if I were to move the base unit up 3 steps, I would divide by 10 3 times. That's not the same thing as dividing by 30. So I divide by 10, divide by 10 again, and divide by 10 again. Okay, so again, it's not the same thing as dividing by 30. Similarly, if I were to start with my base unit and I wanted to convert it to the next unit down, so for example, from meters to decimeters, I would multiply that by a factor of 10. So moving up, divide by 10, moving down, multiply by 10. So again, this is probably going to make a little bit more sense if we take a look at some examples. So again, 1,000 meters. If I wanted to use this stepwise illustration above, 1,000 meters. So meters is my base unit, so I would start in the middle here at the base, and then I would count how many steps it would take to get me to kilometers. So from the base, 1 step up is deca, 2 steps up is hecto, 3 steps up is kilo. And that's what I want. I want to convert it to kilometers. So I would take that 1,000 and divide it by 10 3 times. So 1,000 divided by 10, divided by 10 again, divided by 10 again, and you'll end up with 1 kilometer. Similarly, if I choose a different base unit, grams, instead of meters, same thing. 1,000 grams, I would do the same thing. Divide it by 10, divide it by 10, divide it by 10, and I would get 1 kilogram. And liters, the same thing. That's my base. My base unit for volume would be liters, and I can move from liters to kiloliters by dividing by 10 3 times, which is the same thing as dividing by 1,000. Going the other way, if I wanted to start with my base unit and convert it to smaller units, again, I would have to count how many steps I'm taking down in this case. So my base unit's still in the middle. This time, I'm going down the staircase. And every step I take down the staircase, I'd again multiply by 10. So if I start with, a meter, and I wanted to convert that to decimeters, because I'm moving down the staircase, I'd multiply by 10. So moving up the staircase, you divide. Moving down the staircase, you multiply. So let's take a look at the examples on the right-hand column. I have 1,000 millimeters. Now, 1,000 millimeters puts me at the very bottom of the staircase right here. And I want to convert that to meters. So here's my millimeters. 1 step up would be centi. 2 steps up would be deci. 3 steps up would be back to meters, or the base. So in this case, I would take my 1,000 divided by 10, divided by 10 again, divided by 10 again, and I'd end up with 1 meter. And the other two examples involving milligrams to grams and milliliters to liters are done the same way. So here are a couple of examples of conversions. All right, here we want to convert 9.5 kilograms to grams. So again, let's go back to our stepwise calculation here. I want to convert kilograms, which is way up here, kilograms, and I want to convert that to grams, which is the base unit. So kilograms to grams, because I'm moving down, I want to multiply each step by 10. So kilograms to grams, that's 1, 2, 3. I'd have to multiply 9.5 kilograms by 10 3 times. And that's what I've done here. 9.5 times 10 times 10 again times 10 again, which will give me 9,500 grams. Another way of looking at it is if I want to convert kilograms to grams, I can multiply it by this, which is called a conversion factor, right? And the conversion factor is simply telling me that for every kilogram, there are 1,000 grams in 1 kilogram. So if I have 9.5 kilograms, I multiply it by 1,000 grams in 1 kilogram, and that'll give me the 9.5 grams. The cool thing about doing it this way is if we treat this as a fraction, the 1,000 grams over 1 kilogram, I can cancel out, just like we did. If we have a numerator, a number at the top of a fraction, the number for the bottom of the fraction, I can cancel out the kilograms, just like I would cancel out numbers. So the kg up here and the kg down here would cancel out, and you'll notice the only unit I'm left with is grams. So that's another way of looking at it, right? You can do it either way, going through the stepwise movement and deciding whether you're dividing by 10 or multiplying by 10 each step you take, whether you're moving up the staircase or down the staircase, or you can take a look at this multiplication by a conversion factor, whichever method you choose. So let's take another example into consideration here. Let's take a look at converting milliliters to liters. Okay, get back up to our step. Here's milliliters, and we want to go up to liters. Now I'm moving up, so I'm going to be dividing by 10. That's once. Dividing by 10 again, that's twice. Dividing by 10 again, that's 3 times. So I would go back and 300 milliliters divided by 10 once, divided by 10 again, that's the second time, divided by 10 again, that's the third time, then I would get it in liters. Same idea as a conversion factor. This time, you'll notice that 1 liter is equal to 1,000 milliliters. I put the milliliters, the 1,000 milliliters on the bottom here, because I want these to cancel out. The milliliters up here, the milliliters down here to cancel out, so that I would end up with liters as my answer, my units for my answer. So again, it doesn't matter which way you convert, if you use the conversion factor or if you wanted to do it stepwise and have a kind of a visual. All right, so have that step beside you and you can go from one step to the next. Okay, I'm going to continue with this video. You may wish to pause it, right, and then just work a little bit through some of the conversion questions. But I just want to talk a little bit about scientific notation. Scientific notation is really used to take really large or really small numbers and convert them into something a little bit more manageable. So here, for example, we've got a number with lots of zeros. Okay, so lots of digits in this number. If I wanted to write this using fewer digits, I could recognize that right now the decimal point is right here where my cursor is. If I were to divide this by a factor of 10, I would end up with a smaller number. So for example, if I were to divide this by 10, I would move the decimal place from right here to 1 over. Dividing it by 10 again, dividing it by 10 again, again. So I can keep dividing by 10 and progressively make this larger number a little bit smaller. Now, when we're using scientific notation, we want to do that. We want to divide by 10 until the decimal point is between the first and second digit. I want to end up with a number somewhere between, it's got to be greater than 0, but less than 10. So if I move the decimal point from over here all the way here, I'll end up with 2.6. That is a number that's greater than 0 but less than 10. Now I need to count up how many times did I divide by 10? Well, I divided by 10 once to move the decimal here, twice, 3 times, 4 times, 5 times, 6 times. So if I wanted to get this original number again, I would take 2.6 and multiply it by 10 to the 6. And that simply reverses what I've done before. When I was making this number smaller, I was dividing by 10 6 times to get 2.6. So to get back the original number, I would have to multiply 2.6 by 10 to the, and that's where the 6 comes from, because I moved that decimal place over 6 places. I divided by 10 6 times. We can do that with really, really tiny numbers as well. Nobody wants to write all of these zeros to finally hit these non-zero values here. So instead of dividing by 10 this time, if I were to multiply this number by 10, in essence, I'd move the decimal place 1 over. Multiply it by 10 again, I'd move the decimal place another place to the right. And I keep doing that until I end up with a decimal place right here between the 1 and the 5. That's a number between 0 and 10. So let's see how many times I'd have to move that decimal over to get it to between 1 and 5. So if I move the decimal place over here, that's 1, 2, 3. Well, there's 3 more, that's 6. There's 3 more, that's 9, 10, 11. 11 places is what I would have to move that decimal place to get 1.5. Now you'll notice when I'm going from a really tiny number and shifting the decimal place, I end up with a much larger number. So I need to, if I wanted to take 1.5 and get this really tiny number back, I'd have to take the decimal place and move it 11 places to the left to get this number again. And that's why we've got 1.5 times 10 to the minus 11. Every time I am taking, I've got the scientific notation for a very, very tiny number, I should have a negative exponent. If I've got scientific notation for a really, really large number, I should have a positive exponent. And the reason for that is I need to move this decimal place in the previous example 6 places to the right in order to get this original number. In this second example, I need to move this decimal place 11 places to the left in order to get this really, really tiny number. All right, so let's take a look at the next example. Here's the decimal place right here. I need to move it over 1, 2, 3 places. So 5.62, I've moved the decimal place, times 10 to that. Well, how many places did I move it? I moved it 3 places. If I move the decimal to the left, I'm going to put a positive exponent because I need to multiply this number by a pretty large number, in this case 1,000, to get back the original. If I'm dealing with a really, really tiny number, well, I'm moving the decimal place in the opposite direction. There's 3, there's 6, there's 7. So 1.49 times 10 to the minus 7. When I'm moving the decimal place to the right, I'm going to have a negative exponent. All right, so negative exponents are numbers that are smaller than 1. Positive exponents, numbers that are bigger than 1. All right, so the rules that we just went over are just summarized for you next, and there are a couple more examples, right, that you can take a look through. Now, sometimes it's necessary to round off a number to a certain number of digits, right? And the rounding rule is you look at the number that's to be dropped off, right? So if that number is 5 or greater, then you're going to round the number to the left of it up 1. Okay, so for example, this probably makes a bit more sense when we look at an example. So here we've got 3.4567. We want to round it to only 3 digits. So here would be 3 digits, 1, 2, 3. So I only want to have 3 digits in my answer. So I take a look at the next digit over. The next digit over is a 6. That's greater than 5. So I'm going to round this 5 to a 6. And if I express this number to only 3 digits, it becomes 3.46. If I take a look at the next example, we got 2.9123. I only want to round it to 2 digits. So that's only these two, the 2 and the 9. If I look over to the right of the 9, the next digit is a 1. So I'm not going to round the 9 up. I'm just going to ignore the other digits. So I'm just going to round it to 2.9. We want to take a look at rounding this next one to 4 digits. So here is 2 digits, there's 2 digits, there's 3, there's 4 digits right there. Okay, so next to the 4th digit, to the right of the 4th digit, is a 9. 9's greater than 5, so that's going to cause me to round this 8 to a 9. So when I round this number to 4 digits, it becomes 5.679. All right, you probably want a little bit of time to work, again, so you can pause the video before we talk a little bit about significant digits. All right. So significant digits give us an idea as to how accurate a measurement is. Okay. So, for example, if you are measuring something with a meter stick, right, a stick that's exactly 1 meter in length, but it has no markings on it, then really you can only give an estimate as to the number of meters a particular distance is, right, that you measure using that meter stick. Because there's no measures, there's no other marks on that meter stick, you don't really know how many centimeters a particular object might be. You can only round it to the nearest number of meters. So significant digits kind of tells us how accurate our measurement is. So we'll talk about some rules for significant digits, and we'll as we proceed through the lecture, we'll talk a little bit more about why significant digits are important. So rules for significant digits. If we're thinking about digits that are important, any digit from 1 to 9 is important. Zeros, well, it depends on where they are. They may be significant or they may not. Zeros are only significant if they're within or between two non-zero numbers. Or, and this is an important part too, if they follow a number. Now, the reason these zeros are important is it tells us that we must have had some really precise instrument for measuring this value. Because not only were we able to measure it to the tenths place, we were able to measure it to the hundredths place and the thousandths place. So we're talking about like an Olympic timing mechanism that can measure to the thousandth of a second. So that means that these were actually measured and they were 0 and 0. There's no guesswork here. You use something that actually measured to these decimal places. So these are important to keep, right? Especially if you're trying to compare the times of two athletes. You need to keep these digits in order to see who comes in first, who comes in second, right? And the other placings as well. So this 0 here in the previous example, right, is important, right, because it was one of the measured values. If you're measuring to the thousandth value, you certainly were measuring to the hundredth place as well. All right, so those zeros are significant. Because they are significant, like when we write this in scientific notation, we're going to include these zeros at the end because it tells us that, yeah, we measured to these decimal places. We are certain that this is a 0 value here and this is a 0 value here. Okay, so that's why they're considered significant. Now, here's where it gets a little dicey. The zeros, if they're leading zeros, so for example, if you got a decimal place, then a couple of zeros here, these leading zeros are simply placeholders. All right, we only measured to these decimal places here. So I can rewrite this number as 3.9, just like we did before, right? We were changing numbers using scientific notation. I can rewrite this as 3.9 times 10 to the minus 2. This 0 was really the only function of the 0 is to tell us how far away from the decimal place these two numbers were. So zeros, they're called leading zeros that are after a decimal point and before non-zero numbers are not significant. When we rewrite that in scientific notation, they drop off. This is just 3.9 times 10 to the minus 2. So that tells us that we can't just willy-nilly just add zeros. So for example, I can't make this 3.900 times 10 to the minus 2 because if I look at the original number, we didn't measure to those places. We didn't measure to those place values. So I cannot just arbitrarily stick in extra zeros in a number. So each 0 indicates that degree of measurement, that degree of accuracy. So if you were to do something like this, 4.32000 centimeters, that means that you've got an exceptional ruler, and that ruler is able to measure to 1/10,000th of a centimeter. So we can't just randomly tack on zeros to a number. Okay, it has to do with certainty. So a decimal place indicates more certainty. So for example, if we take a look at this value, this means that this was measured to the tenths of a kilogram. This is more precise. This is a more precise measurement than 2,500 kilograms because this is just rounded to the nearest kilogram, right? I don't know if it's 2,500 point 0.3 kilograms, could be zero point 0.2, right? Because all I'm certain of is that it rounds to 2,500. Whereas here, this number tells me it's 2,500 and 0 tenths. So it's measured to the tenths. All right. Now, these numbers here, after the 25, they serve only to place the decimal, tell us how big this number is. So I can rewrite this in scientific notation as 2.5 times 10 to the 1, 2, 3. 2.5 times 10 to the 3, and that would only have two significant digits. Let's take a look at some examples, and they'll become a little bit clearer. In this first one, we've actually got 4 digits, right? And this 0 is in the middle of non-zero digits, so I'm going to count all 4. That's 4 significant digits. This one, all 3 of these are important. It's got 3 significant digits. This one, remember we said the leading 0 is not significant. Not significant, so here I only have 2 significant digits. 2 significant digits. Here, there's only 1 digit, so 1 significant digit. This is not a leading 0. This tells us that we've actually measured to the tenths place. So I've got the 2 and the 0. Both of them are important. So those are 2 significant digits. Next example, here we've got 3 significant digits. This one's only got 2. And this one has got 1, 2, 3, and 4 significant digits. So 4 significant digits there. So when we're doing calculations involving significant digits, here are the 2 simple rules you're going to follow. Whenever you're adding or subtracting, we look at the number of decimal places there are. So in this first example, I've got 1 decimal place in this number, 2 decimal places in this number, 3 in this number. Now, I can only be 100% sure of the tenths place. I don't know what the other values here might be because we didn't measure it to the hundredths place or thousandths place. Over here, we measured to the hundredths place, but there could be a number between, 1 and 4 that's here. And it wouldn't change the value of this if it's written to just 3 decimal places, to 3 significant digits, 3 digits. Because with rounding, this next number could have been a 1, could have been a 2, could have been a 3, could have been a 4, and we would still round it to 3.21. Next one, well, this is this is the most precise measurement here because we've actually measured it to the tenths, hundredths, thousandths place. But when we add these numbers together, we can only really be certain up to this decimal place, right? So this is the least precise measure. So we're going to take a look at the least precise measure, take a look at the number of decimal places it has, and that's what we should express our answer to that many decimal places. So you count up the number of decimal places in each of the numbers you're adding up, pick the lowest one, okay? The lowest one, that would be this one, and that would be the number of decimal places you'd have in your answer. Okay, so taking a look at another example here. This time we've got 2 decimal places in the first, 3 in the second, and 4. Again, I'm counting up and comparing them. 2 is the least number of decimal places, so my answer, when I add them up or subtract them, should have 2 decimal places. Not significant digits, 2 decimal places, 2 numbers after the decimal. Now, this is different than multiplying and dividing. When we're multiplying and dividing, we want to count up the number of significant digits. So here I've got 1, 2 significant digits. Here I've got 3. I then perform the calculation, whatever it is, a multiplication or a division. I'd get my answer but then I would express my answer to the fewest number of significant digits.